Welcome to the van der Waals equation. So we can draw conclusions from the virial equation of state only by inserting specific values for the coefficients. But we can generate a more general, if less precise, equation of state. So J.D. van der Waals did this to formulate his van der Waals equation of state, which we have here. So now we have P is equal to nRT over V minus n times B minus A times n squared over V squared. And this is often written in terms of the molar volume. So pressure is equal to R times T divided by the molar volume minus B minus A over the square of the molar volume. And note that those constants A and B are the van der Waals coefficients. And these are different for each gas, but they are now independent of the temperature. So A represents the strength of the attractive interactions between the molecules, and B represents the strength of the repulsive interactions between the molecules. So let's look again here. We said A represents the strength of the attraction between the molecules. So as A gets larger, the pressure is going to be smaller, which makes sense. If A is representing the strength of the attractive forces between the molecules, as those attractive forces get larger, the pressure exerted on the walls of the container should decrease because those molecules are attracting each other, and thus they're not pressing against the side wall as hard. B, we said, represented the repulsive forces between the molecules, which makes sense. As B gets larger, then pressure gets larger, because B is being subtracted from the molar volume, which means that as B gets larger, the denominator here gets smaller. As the denominator gets smaller, that value of that fraction gets larger, and that means the pressure becomes larger, which again makes sense. If the molecules are more repulsive, then they're repelling each other more. That means that the pressure exerted on the walls of the container will be higher. Furthermore, the effect of these interactions, the effect of B and the effect of A, becomes larger when the molar volume, Vm, becomes small. Because as Vm becomes smaller, then B becomes a larger fraction of Vm, and A becomes a larger fraction of the square of Vm. Now, there are other such approximations for the virial equation of state, and they each have strengths and weaknesses. Now, we can judge the reliability of the van der Waals equation by comparing isotherms it produces to experimentally measured isotherms. So the isotherms produced match the experimental isotherms quite well, except for the oscillations or van der Waals loops at temperatures below the critical temperature. So those are these loops here. So note that the numbers we've got written here, 0.8, 1.0, and 1.5, are the values of the temperature as it is divided by the critical temperature. So 1.0 represents the isotherm at the critical temperature. So these loops are unrealistic because they predict that a decrease in volume causes a decrease in pressure, and vice versa. That is, at some point in this regime, as we decrease the volume, we decrease the pressure. Now that doesn't make any sense. That's going to violate Boyle's law, and thus we've got some problems there. We need to get rid of this van der Waals loop. So to fix this issue, we can use a procedure called the Maxwell construction. That is, we draw a horizontal line on the isotherm such that the loops define equal areas above and below the lines. So if we've got our isotherm here, we adjust the position of this horizontal line such that the area over there, the area below that line, is equal to the area above the line. And that means that the actual line that we're going to be looking at goes from here, and then it goes straight across, and then the pressure goes up again. So we never get a case where decreasing the molar volume will decrease the pressure. And note that this behavior now matches that we saw when we were looking at the example of carbon dioxide, where we have the pressure initially going up, and then at some point we start to condense, and the pressure stays the same, and the plunger just keeps going in until we get all of our gas condensed to the liquid phase, and then the pressure shoots up again. Those are for temperatures below the critical temperature. At the critical temperature, we just get a supercritical fluid, and so at temperatures above that, we just get that supercritical fluid. We never actually condense the liquid out, and that's why we don't have to do this Maxwell construction at those higher temperatures. Now, we can summarize the major points of the van der Waals equation. At high temperature and large molar volumes, the isotherms generated match the ideal gas isotherms. When temperature is large, the first term in the van der Waals equation is much larger than the second term. And when the molar volume is large, then the molar volume is much, much larger than B, and that means that the denominator of the first term approaches the molar volume, and that then gives us the ideal gas law. Now, liquids and gases coexist when cohesive and dispersing effects are in balance. And the van der Waals loops occur when the two terms are similar in magnitude. The first term arises from the kinetic energy of the molecules and their repulsive interactions. And the second term arises from the attractive interactions of the molecules. Now, the critical constants are related to the van der Waals coefficients. For temperatures below the critical temperature, the calculated isotherms oscillate and each passes through a minimum and maximum. Now, as the temperature approaches the critical temperature, the minimum and maximum then converge. They get closer together. And at the critical temperature, then there is no local min or max, but instead a horizontal inflection point. Now, since a horizontal inflection point arises when the first and second derivatives are zero, then we can say that dP dVm is equal to minus RT over the square of Vm minus Vb plus 2a over the cube of the molar volume, and that has to be equal to 0. And we know that the second derivative of pressure with respect to the molar volume is equal to 2 times RT over the cube of the difference between molar volume and B plus 6a over Bm to the fourth, and that also has to be equal to 0. Now, if we work out the solutions to these two equations, we get the critical volume is equal to 3 times B, the critical pressure is A over 27B squared, and the critical temperature is 8A over 27 times R times B. And we can then find the critical compression factor Z sub C, which is given here. Now that's going to be equal to 3 over 8, so 3/8. Now, actual critical compression factors are smaller than 0.375. They're generally about 0.3, but the van der Waals equation gets close to the experimental values. Now, it's often useful to compare the property of an object to a related fundamental property of the same kind and set up a relative scale on that basis. So we can use the critical properties of gases to calculate dimensionless reduced variables by dividing the actual variable by the critical constant. So the reduced volume is the molar volume divided by the critical volume. The reduced temperature is the actual temperature divided by the critical temperature. The reduced pressure is the pressure divided by the critical pressure. And note that these properties are dimensionless and have values near-ish to 1. Now, van der Waals hoped that gases confined to the same reduced volume at the same reduced temperature would exert the same reduced pressure. And this is largely true as the variation is small for a range of gases. So the curves over here are labeled with the reduced temperature. So we've got a reduced temperature of 1, 1.2, 2.0. And so down here we've got the reduced pressure, and here we have the compression factor. And the blue ones, the blue circles here represent nitrogen, the yellow ones are methane, the green ones are propane, and the purple ones are ethene. And so you can see that on each curve representing the isotherm, the various dots of different colors, so the different substances, are all pretty darn close to that curve. So van der Waals was close. So the observation that real gases gases at the same reduced volume and reduced temperature exhibit the same reduced pressure is called the principle of corresponding states. And this principle is only an approximation that works best for spherical molecules. The approximation fails, and sometimes pretty spectacularly, when the molecules are non-spherical or they're polar. The van der Waals equation can be expressed in terms of our reduced variables then. So the reduced pressure times the critical pressure is equal to R times the reduced temperature times the critical temperature times the reduced volume times the critical volume minus B minus A over the square of the reduced volume times the square of the critical volume. And we can then substitute the values for the critical constants in terms of A and B to give us this, which we can then rearrange to give us this. So now we have the reduced pressure is equal to 8 times the reduced temperature divided by 3 times the reduced volume minus 1 minus 3 over the square of the reduced volume. And note here that A and B, which vary from gas to gas, have now disappeared. So this now applies to all gases. And thus, we expect the sort of diagram that we obtained earlier for the different gases. And that was the van der Waals equation.